Hi, everyone. So this video is going to help you work through the first part of experiment 6. And so for our experiment 6, electrochemistry, this is a 2-week lab. And part 1, as we'll see, is really an extended worksheet to sort of overview the content of the electrochemistry we'll cover in lab. And then next week, we'll actually perform the experiment. And so as you scroll down your lab handout, as he's printed it out, you can see here's overall instructions. We're going to break the lab into 2 parts. So this week is our week 1 consists of answering the initial questions, and then week 2 will be the data collection. And so just so we're clear, as you scroll down for today's lab, what we need to be doing is completing pages 3 through 7. So that is starting with the page galvanic cells and cell potential. And I'll just scroll down to show you where the end of this is. So this is page 3, and we're going to go all the way to page 7. So these are all the questions we'll have to answer today. And getting all the way down to, there's page 6. And then finally, here's page 7. And so this will be our last question that we should be answering. So everything above here we'll have to answer. And then all of this will be turned into a PDF, these pages, and submitted to Canvas. And you can see submit it to the Experiment 1 Week 1 submission box as a PDF. And this is our lab activity for today. So please submit this today. And these calculations and these questions will help us with our data analysis next week. Since we can't meet in person today, I'm going to sort of walk you through this worksheet. And if you have questions when you're running through it, please send me an email and I'll be happy to sort of try and help you. As you can see in the information in the introduction, a couple sections of useful information to help you answer these questions are going to be section 16.3 of your textbook, right? And also the appendix L of our OpenStax textbook. I just want to show you those 2 things. So if I have them open on my web browser, so here's section 16.3, and this will cover a lot of the same content that the lab will be covering. So you can use this as a reference to sort of how to do things. They have some cell diagrams, some tables of reduction potentials. And then we have our appendix L. And so in the appendix L, you'll have to use this appendix to search for a couple particular half reactions and their reduction potential. And I'll point that out to you in a minute, but please know you're going to have to refer to the textbook for this. As you're working through this, I would strongly encourage you to try and find your classmates and your peers and work together in groups. If we were together in lab, you would be in groups of 3 or 4 talking through this, and I'd be there answering questions. So in lieu of that, try to find your peers and work with them and send me emails, and we can even set up a Zoom if you have questions on things. Okay. So let's walk through this. A couple pieces of information. So in question 1, you're asked to figure out what the standard conditions are for our electrochemical cells. So again, you can find that by going to section 16.3 of your textbook, and then you can fill in the relevant information in these blank spaces. As you're working through, one of the important equations we're going to have for us is this one shown here, where delta G naught is equal to negative NFE. And we could write an analogous equation at non-standard conditions and say delta G is also equal to negative NFE if we're at non-standard conditions. And this is going to be a really important equation for us to use. And in part A, we're asked for a spontaneous process. Will E naught be positive, negative, or 0? And we can do that by remembering that a spontaneous reaction has a negative delta G. And so if we have a negative delta G to make it spontaneous, what must the sign of E be to have overall delta G be negative? You can think about that, and that'll go here. When you have that answer, then we could go to B and C. And for B and C, it's going to ask us to go to Appendix L. And in Appendix L, we have our table of standard electron potentials, our reduction potentials. And on table L, you're going to have a list of E naught values for a half reaction. And so which values on table L would represent a favorable half reaction? Which values on table L would represent when do you get delta G as being less than 0, right? That's what we're looking for. What magnitude, size, sign of E gives you the negative delta G? And then by contrast, in part C, which reactions would represent an unfavorable reaction or give you a delta G greater than 0? Again, I'm looking for the sign of E, the magnitude of E, to help answer those questions. All right. In question D, right, we're looking at this table of standard reduction potentials. That's Appendix L. Okay. And what this question is really asking is, how can you use that table of reduction potentials to determine which reactions are most likely to stay as reductions and which reactions are most likely to go as an oxidation? And so if I go back to that table for a second, when you look at this table, in our E naught values, we have our values of our cell potentials. If you look at the half reactions, every reaction listed here is a reduction. It's always something plus electron goes to something else. If we make an electrochemical cell, we know we have to have one reaction that's an oxidation and one reaction that's a reduction. So one of the reactions that's written as a reduction has to be flipped around and turned to an oxidation. And so how can you tell? If you have two half reactions and their reduction potential, how can you use the value of E to figure out which one is more favorable and which one's less favorable? And the less favorable one will have to flip around and turn into an oxidation. Okay. If you have questions, again, please let me know. Now in question 3, now we're given our first reaction to consider. And we're going to look at a cell that's made of two half reactions. And you can see it's a zinc and copper cell. Again, both half reactions are written currently as reductions. And so the first thing you have to do is use Appendix L to look up the cell potential for each of these half reactions. So you can find these reactions in Appendix L and put them in. And then using your values here and the answer you gave to D, you need to indicate which one of these reactions would get flipped. So one of these reactions will be an oxidation and will actually run in the reverse direction, right? And that's what we want to know. Which one of these is going to go in the reverse direction? Once you know that, we can now write our overall balanced chemical equation, right? By adding the two reactions together, taking note that one of them must have been flipped around. So it's an oxidation. And so all of your electrons will cross out. So we have 2 electrons and 2 electrons. So currently they're both on the reactant side. So 2 of those need to be on the product side after you flip them, so they cross out. When you have your overall balanced chemical equation, we can now imagine a schematic of our cell. And again, go read section 16.3 to help you answer these questions. But here's our electrochemical cell. And we have to figure out which side is so is this the anode or is this the anode? Where is oxidation taking place? Is zinc oxidized or is copper oxidized? Okay. Whichever one's oxidized is your anode. And electrons always flow. So electrons will flow from the anode to the cathode. And so they'll flow along the wire. And so your electrons will either flow this way along the wire to the electrode, or they'll flow this way along the electrode wire. And so that's what we're kind of looking for as you go through that. Part E is going to ask us now to calculate the overall cell potential, right? And so we can take our reduction potentials you found here. So your reduction potentials, these two reactions, and you can calculate your overall cell potential using that. When you have your cell potential, part F is going to ask us to calculate the Gibbs free energy, delta G. And remember, as you go through this, delta G naught is equal to negative NF E. And in your equation, E, cell potential, was from part E above, right? So this came from the question right here. F is a constant, so we know F. And N is the number of electrons transferred in this reaction. So that number of electrons transferred is going to come from your overall balanced chemical equation. And we can see we have a 2 electron transfer process because we have 2 electrons lost and 2 electrons gained. So 2 electrons. So 2 for N for this problem. Okay, so that gets us through page 4. Starting in page 5, we're going to look at another equation that's known as the Nernst equation. And this is a relationship between our delta G at non-standard conditions equation, which we looked at before, delta G equals delta G naught plus RT ln of Q. And through some substitutions, right, we can say, substitute in for E and do some algebra, and we can remake this equation in the form of our cell potentials and say E cell at non-standard conditions is equal to the E cell at standard conditions minus RT over NF ln of Q. This equation can then be rearranged a little bit more, right? And turned into this equation here, right? It's the same equation. We've just manipulated it a little bit. And the question is, why do we do this? Why did we rearrange this? And it's because we put it in the form of y equals mx plus b, right? And using this, what we've done is we've put our equation in the form of a line. This will allow us to graph and to come up with a straight line plot. And so that is what I want you to sketch down here. You're going to sketch a straight line plot. And I want to know, as you sketch this plot, right, what are your axes labels, right? And then is your straight line plot look like this? Or does your straight line plot look like this? And in order to answer that, you need to go to the form of the Nernst equation here. In part B, we're going to look at this part of our equation, which is up here. Okay. And what we're going to do is we're going to simplify it, because if we look at this part of the equation, R, T, and F and 2.3 are all constants. And so what we can do is just on our calculator, simplify this by sort of doing the math on all of our constants and leaving this in terms of N. So if we take 2.3 times R times temperature divided by F, we'll be left with some number still divided by N. And so we can take that whole expression, and instead of having all those constants, we can end up with some expression that's going to be negative, whatever you get for a calculation, divided by N. It's just a way of simplifying this expression by combining all those constants. And so you have to figure out what is that numerical value that would go here. We're then going to look at that, say, in part C, ask ourselves, well, this term here, what is it with respect to this plot, right? what is this term on your plot, right? Is it the slope? Is it the y-intercept? Is it your x value? Is it your y value? What is it with respect to the plot? Okay. So in question 5, okay, we're going to again look at the same equation, right, which you've already done some manipulation with. And for A and B, you don't even really need the equation. This is just from our previous knowledge. And just remind ourselves, if Q is less than K, are we moving to the right in a chemical equation or to the left? Right? And that answer would go here. And then based on our answer, we can say, is the reaction spontaneous? And then in part B, we're going to do the same thing, but go in the reverse direction. If Q is greater than K, are we moving to the right or left? And does that mean your reaction is spontaneous or non-spontaneous? In part C, we're asked when we are at equilibrium, so if Q is equal to K, we can recall that delta G is equal to 0, okay? And if delta G is equal to 0, what is E cell? And remember, when you go through this, we know delta G equals negative NFE. And so if delta G is 0, then E cell must also be 0. With that in hand, in part E, what we're going to do is we're going to take this equation and we're going to rearrange it. And we're going to do some algebra. And what it's saying is when Q is equal to K, can we rearrange that equation and solve for the equilibrium constant? And so I'm going to set this up and do the first step for you. So remember, we know when Q is equal to K that E cell is 0. So actually, I'll rewrite the whole thing so we can see each step. We have E cell equals negative. And I'm going to put this 2.3 RT over NF here, right? Times the log of Q plus E naught cell. Now, when you do this, this term here, instead of writing all of that out, you can go to your answer to B, and you can put that answer for B in instead. But if we come back now, we're going to say, well, okay, what do we know? And again, we're looking at when Q is equal to K, E naught cell equals 0. And so I'm going to substitute in 0 for E cell equals negative. Again, this is what your answer from above, but I'll just put the constants in for now. Times the log of K plus E naught cell. And so now what we need to do is we have to rearrange this equation, because what we want in the end is an equation that says K is equal to, and we need some algebraic expression. This is what you're looking for, right? So to do this, we have to remember our algebra rules. So the first thing you'll have to do is subtract E naught cell to the other side of the equation. Then we're going to have to divide or multiply by the reciprocal of what's in here to isolate log K. And then we're going to have to get rid of our log. And to get rid of the log, we do 10 raised to whatever is there. And so you can set that up. And so in the end, what you'll see is your K equation is going to be in the form of 10 raised to some exponent here. And that's really what you're solving for. If you have questions, let me know. Okay. In the last part, we're almost there. Starting with question F, we have a new chemical reaction. Okay, we're looking at two two half reactions. We're going to combine them together to make an electrochemical cell. And so when we look at this, we have the reduction potentials for both of these. One of these reactions, they're both written as reductions. One of these has to be an oxidation. So we have to use our potentials here. And again, go up above to remind ourselves which cell potential do we keep and which do we flip by comparing our two numbers. So one of these will end up being an oxidation. Once you figure out which one, you can flip that reaction, and then we'll have to add these together to get the overall balanced chemical equation. Once you have the overall balanced equation, then we need a equilibrium constant expression, KEQ, which is again products over reactants, and that's going to be based on your chemical equation you get here. When you have that, we want to calculate the equilibrium constant, your KEQ, and we're going to use our E naught cell that you calculated from here and your equation you derived up here. So we're going to use the equation you derived from part E with the cell potential you calculate from your two half cell reduction potentials to calculate K to get a numerical value here. Based on the magnitude of K, we can say, is our reaction spontaneous or non-spontaneous? Remember, if you have a really big K, it's a spontaneous reaction. If you have a really small K, it'd be a non-spontaneous reaction. So that's what we're kind of looking for. In part J, we're going to switch it up a little and look at an analogous chemical reaction. And in this case, we're going to write an equation for the dissolution of silver chloride and a KSP expression. So remember, for KSP, we're always starting from the form of the salt, and we're writing an equilibrium arrow to break it into the respective ions. And so here would be the chemical equation we'd want. And now we have to write our equilibrium constant expression. When we have this, we can compare this equilibrium constant expression to the equilibrium constant expression you got here. And ultimately, what we're going to do in part K is we're going to try and get a numerical value for KSP. So calculate the KSP. So we want KSP equals, and we want a numerical value. And we have to get that from comparing what is the mathematical relationship between this, the numerical value you got here, and the relationship here. And there's some sort of hints to sort of help you do this. Again, if you have questions, let me know. This little self-check for you is with the KSP expression here. Remember, silver chloride is an insoluble salt. And so we can think about, should this equilibrium constant be big or small? And did you get a big or small equilibrium constant here? So this is a lot. This is not an easy worksheet. Please ask questions. Watch this video a few times if you need to. Work together, and just let me know how I can help you with this. When you're done, please convert this all to a PDF, submit it to Canvas, and we'll see you soon in class. Thank you.